In this work, we study motion deblurring for thermal videos. Thermal cameras, specifically microbolometers, can enable robots to see in absolute darkness by imaging the heat radiated from the scene. Yet, their usage in robotics has been limited by motion blur. Motion blur occurs when imaging fast-moving objects and in low-light conditions where long exposure times are needed. Consider this image of a well-lit scene captured with a panning camera. There is no motion blur. However, the corresponding thermal image is significantly blurred despite the higher frame rate used in the microbolometer. While visible cameras allow us to control exposure time to limit motion blur, microbolometers are always exposed to the scene. Furthermore, a frame is considered a snapshot of the scene, but microbolometers do not have a counter that resets to 0 at the end of a frame. In this paper, we want a motion deblurring algorithm that respects the physics of image formation in microbolometers. It must work for arbitrary camera motions as well as handle dynamic objects in the scene while achieving state-of-the-art performance. Consider a simple scene of a ball moving in circular motion. A visible camera image is obtained by averaging the light collected during the exposure. On the other hand, each microbolometer pixel is always exposed to the scene and its temperature is governed by a first-order differential equation. Now consider the pixel marked by X. The true temperature of the corresponding scene point is a square pulse plotted in blue. However, the temperature returned by the pixel, shown in red, exponentially decays and grows, much like a resistor-capacitor circuit. The cumulative result of this effect at all the pixels appears as motion blur. Clearly, the difference in the underlying physics is reflected in the distinct appearance of motion blur in these two sensors. In the literature, motion blur is typically modeled as a 2D spatial convolution where I is the blurred image, h is the point spread function, and L is the latent image of interest. Both h and L are unknowns. Note that h explicitly models the relative motion between the camera and the scene. We instead approach the problem purely in temporal domain pixel-wise. This is a closed-form solution for microbolometers where tau is a fixed camera parameter. Notice the absence of h and the only unknown is the latent image L. In our paper, we formulate a convex optimization problem to estimate L from a sequence of high frame rate measurements. Now to some results. Consider this dynamic scene where the camera's panning motion is in sync with the motion of the car. There are two pedestrians walking close to the camera and several pedestrians in the back. A single frame from this sequence exhibits highly non-uniform motion blur. Here, we show the result of a strong baseline, deblurred, which is a learning-based algorithm. Although the image appears deblurred, it produces unnatural artifacts, fails to recover the bicycle frame, and does not preserve the depth ordering of the scene. In comparison, our proposed algorithm provides superior results without any artifacts, while correctly recovering that the pedestrian is in front of the car. In another example, the camera undergoes a rolling motion while several pedestrians are walking across. Notice that the pixels on the left and right edges of the image experience greater blur than the pixel in the center of the image. Deblurred fails to remove the large motion blur, while our pixel-wise formulation faithfully removes the motion blur in all portions of the image. For quantitative evaluation, ground truth images are typically collected using high-speed visible cameras, but this cannot be replicated for microbolometers. Instead, we collect a blurry thermal dataset encompassing several challenging scenarios for motion deblurring algorithms. We annotated cars and pedestrians in over 400 such images. On this test dataset, we computed the object detector accuracy on the blurred images and on the images restored using different deblurring algorithms. We consider the change in detection accuracy as a proxy for performance of the deblurring algorithm. Our approach significantly outperforms all learning-based single and multi-image deblurring algorithms consistently for several detectors. In summary, our key contributions are: we formulated a motion deblurring algorithm that respects the microbolometer physics. Our pixel-wise formulation is capable of handling arbitrary camera motions and scene dynamics. And our model-based algorithm significantly outperformed state-of-the-art deblurring algorithms.